Okay, today we're going to continue with permutations and start with combinations. Let's review the formulas we had last time for permutations. If you permute n objects and they're all distinct, we said there are n factorial permutations. If you permute r from n, we said there are pnr, and we gave two formulas for pnr. One was n minus 1, all the way down to n minus r plus 1. And the other formula for pnr was n factorial divided by n minus r factorial. Now suppose the objects are not all distinct. Suppose that some of them are repeated. Then we don't have quite as many permutations as we do when they're all distinct, because many of them are not recognizable. For example, suppose I want the permutations of AAB. That is a listing of all the recognizable different permutations of AAB. Then we have AAB, ABA, BAA, and we see there are only 3 permutations, where in fact if they were distinct, I would have had 3 factorial or 6 permutations. So I have fewer permutations. If I had to permute these 5 objects, and again the A's and B's don't have to be letters, they could be people, they could be all kinds of objects, anything you may want to permute, arrange in the store window, or items that you select. If they were all distinct, I would have had 5 factorial, 120 permutations. But they're not all distinct, I have fewer permutations. Now how many fewer? Well, I know that these 3 objects, if they were different, allow 3 factorial, 6 permutations. So really now I only have 1/6 of the permutations allowable because of the A's. And these B's, if they were different, would have allowed 2 factorial, or 2 permutations. Now I only have 1/2 because of the B's. So instead of having 5 factorial, 120 permutations, I have now 5 factorial over 3 factorial times 2 factorial. That is, I divide what I would have had by 3 factorial, because that accounts for all the A permutations, and by 2 factorial, that accounts for all the B permutations. In general, if we have n items comprised of so and so many of one kind and so many of another kind, then the formula looks something like this. Etc. Up to some last index I'll call R sub t of the teeth kind. Then we have the following formula. The number of permutations of n objects R1 of one kind, R2 of another, up to RT of a tth kind is given by n factorial, and for each of these r's you divide by that r factorial. Okay? Now, the exact derivation, I sort of gave a general derivation of that. The exact derivation, perhaps we'll do at the end of the tape, and if you're interested, you can stay tuned and watch. Let's take some examples of this formula, however. So let's see now. Suppose I did have A, B, B, and I'd like to know how many permutations can I make of this group. Now I know, again, if they were all different letters, I would have had 5 factorial permutations. Here, however, I have 5 objects, 3 of this kind, and 2 of this kind. So I arbitrarily label R sub 1 as 3, R sub 2 as 2. I could have labeled it the other way. It doesn't matter. And the formula says that P, 5 objects, 3 of one kind, 2 of another, is given by 5 factorial divided by 3 factorial and divided by 2 factorial. Let's work this out. 5 factorial is 5 times 4 times 3 times 2 times 1. And I divide by 3 factorial, which is 3 times 2 times 1, and also by 2 factorial. So 3, 2, 1 on the bottom cancels 3, 2, 1 on top. And the 2 of this cancels 2 of the 4. So I just have 5 times 2. And AAABB allows 10 permutations. Let's take another example. Suppose I had 7 numbers and they looked like this. How many different digits could I get from these 7 numbers? Again, if they were all distinct, I could have gotten 7 factorial over 5,000 permutations. Now, however, I have 7 objects, 4 of the first kind, 3 of the second kind, and the number of permutations is 7 factorial over 4 factorial, 3 factorial. Now, I really don't have to write out the entire 7 factorial because I know something on the bottom is going to cancel part of that. Well, what's going to cancel it? 7 factorial starts at 7, goes down 7, 6, 5, 4, 3, 2, 1. But as soon as it becomes 4, 3, 2, 1, it'll be canceled by the 4 factorial here. So these two will give me 7, 6, 5. I go no further because the 4, 3, 2, 1 is canceled by this 4, 3, 2, 1, but I still have this 3 factorial. Now on the bottom, this is 6, cancels this 6, and the answer is I have 35 distinct permutations, recognizable permutations. Okay? Let's take another example. Suppose that you were in a TV store and you had to arrange some television sets for display. Let's say you had 2 Sonys and you had, let's say, 3 RCAs, and let's say 5 GEs. How many ways could you arrange these? Assuming that the Sony sets cannot be told apart from the Sonys, the RCA from the RCA, and the General Electric from the General Electric. So you have 10 objects. You have 3 different kinds now. The first kind consists of 2 objects, the next of 3, and the third kind, 5 objects. So the total number of permutations is P10 semicolon 235. That's 10 factorial over 2 factorial, 3 factorial, 5 factorial. Now the 10 factorial and the 5 factorial, rather than write them all out, I know that as soon as the 10 gets to the 5, 5, 4, 3, 2, 1 will be canceled by this 5, 4, 3, 2, 1. So I have 10 times 9 times 8 times 7 times 6, and I still have 2 times 1 and 3 times 2 times 1 for the 3 factorial. So again, 10 and 5 together give me just 10, 9, 8, 7, 6. And I still have the 2 factorial and the 3 factorial. So this gives me 10 times 9. This 2 I can cancel or divide into the 8, giving me 4. And this 6 will cancel this 6. So it's 90 times 28, and that is 2,520 distinct permutations. Suppose that I wanted to allow everything to move, but I wanted to keep all the RCAs together. How many permutations do I have now? How many perms with the R's together? What I do know is I consider the R's as one unit. I consider these R's as one unit, as if they were tied together into one unit. So now, effectively, I have the following. I have S, S, R, standing for all those 3 R's. So the number of permutations with the R's together is now the permutations of 8 objects, 2 of the first kind, 1 of the second kind, and 5 of the third kind, and that allows eight factorial over 2. So this equals 8 factorial over 2 factorial, 1 factorial, 5 factorial. And the 8 factorial and the 5 factorial will partly cancel each other out, and I'll get 8 times 7 times 6. And on the bottom I have 2 times 1 for the 2 factorial. And the 1 I don't have to bother writing down, it's just 1. 1 factorial is 1. So 2 goes into 6 3 times, and I'll have 8 times 21, 168 distinct permutations. Now this is a useful formula and leads to all kinds of interesting computations. For example, suppose that you're standing at an intersection, let's call it 0, 0. You're standing right here. and you have a friend who's standing here. You might think the horizontal are streets and the vertical are avenues or whatever. And you'd like to go and meet your friend from 0 to 0, 0, 0 to 5, 4. How do you get there? How many ways can you get there? How many ways are there to go from 0, 0 to 5, 4? Well, let's take a sample way. You might take this road. So what are you doing? You're going to the right 2 blocks, and you're going up 1, 2, 3, 4 blocks. And then you have to go to the right 3 more blocks. That's one way of doing it. Or you could go, let's say, up 2 blocks, to the right 2 blocks, up 1, to the right 3, and then up another. In that case, you would be going up, up, right, right, up, right, 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 up. And so on and so on. Now, how many ways are there to do this? Well, whatever way I choose, I must have these 9 letters there. That is, I must walk to the right 5 blocks and up 4 in some permutation. So that's just what we've been discussing. That's the formula. I have 9 objects, in this case 9 directions, if you will. 5 of them are R's and 4 of them are U's. How many ways are there to do that? Each way will give me one way to get from 0, 0 to 5, 4. So we have the number of permutations of 9 things, 5 of one kind, 4 of another, that's 9 factorial over 5 factorial, 4 factorial. Again, the 9 factorial and the 5 factorial are going to partially cancel each other out. I only will go down to 6 on this because as soon as I hit 5, 5 factorial is going to cancel it. And I still have the 4 factorial there. Now 4 factorial, part of that is a 3 factorial, which is a 6. We'll cancel this 6. And I can divide 4 into 8 and get 2. So I have 18 times 7, which is 126. And this formula has many other uses. So we now have 4 permutation formula. We have n objects all distinct, n factorial. We have 2 formulas for P and R, the second of which is, and we have the formula for n objects where they are not all distinct, and you get that. Now, permutations are arrangements of things, but we don't necessarily always want to know how many ways we can arrange things. For example, if you're playing a game, let's say there are 5 people in the room, and the game consists of 3 people going out to share a secret, whatever. You really don't care about the arrangement of those 3 people. You just want to know which of the 3 are going out. Or let's say you want to pick a committee from your class. Let's say the class is 20 people. You want to pick a committee of 5. As long as you don't specify, let's say, president, vice president, etc., you just want to know who's included. That's not a permutation anymore. We call these combinations. And a combination let's write down combinations. A combination is a grouping without regard to order. That is, I would just like to know who's included in this set, who's included in the combination. I really don't care about the order of the people. Now, in a combination, usually you choose R out of n. Again, you have n objects, and again, we assume they're distinct. And you want to make a selection of R objects, but you don't care how they're permuted. So we have n objects. Select R. For example, 3 objects. Let's call them A, B, C. Select 2. How many ways could I do that? Well, I could pick A and B. I could pick A and C. And I could pick B and C. And there are just 3 combinations of 2 from 3. You'll remember that there were 6 permutations. There are more permutations. In fact, how would I get the number of permutations? I could take each combination and permute it. You see, each of these 2-letter items would allow 2 permutations, so that the total permutations would be 2 times 3. There are 6 perms, there are 3 combinations, 6 permutations. Each combination would allow a permutation. Let's take another example. Suppose I had 4 objects, and let's say I choose 2. How many combinations do I have? Let's say the objects are A, B, C, D. 2 at a time. So I could pick A with B, and A with C, and A with D. And since this is a combination, I don't permute these. This is all I have. Then I could take B with C, B with D, and finally I have 6 combinations. Now let's get a formula for this so we don't have to write it out all the time. And again, I'll give you the formula. I'll put the formula down, and for derivation, we'll wait until the end of the lecture and we can derive it. Before writing down the formula, there's a convention that zero factorial is equal to 1. But the reason that this is so comes from a higher function in mathematics, the gamma function, of which factorial is just a particular instance. But the definition is needed for the formula for CNR. In fact, it might even come up in PNR. When you have 0 factorial, you should put a 1. The formula for the number of combinations of R objects from N is N factorial over R factorial N minus R factorial. And this is the number of combinations selecting r from n. So we're already used to dealing with factorials. Let's take a few examples. Let's take the one we did over here, which was n equal 4 and r equal 2, and see if we get the number 6. We have c 4, 2. So n is 4 and r is 2. So on top goes n factorial, that's 4 factorial. Then we have r factorial. Since r is 2, this is 2 factorial. And we still have to divide by n minus r factorial. Now, since n is 4, r is 2, this number is 2 factorial. Now, 4 factorial is 4 times 3 times 2 times 1. Will be canceled in part by one of these. Let's say this one, 2 times 1. So it just leaves me 4 times 3. And I still have this 2 times 1. And indeed, we get the number 6. That is, there are 6 ways of choosing 2 from 4. For example, if you have, let's just say, 2 couples, man-wife and a man-wife, how many relationships are there among these 4 people? Well, a relationship means 2 people, so there are 6 relationships among 2 couples. Or if 4 people introduce themselves by handshake, say, how many handshakes are needed? 2 from 4. 6 handshakes will introduce everybody. Let's take another example. How much is C 5, 3? It's a number of ways of choosing 3 objects from 5 objects. It's n factorial. If we define 5 as n, r is 3, over 3 factorial. And the difference of these two is 2 factorial. Now 5 and 3 will just leave 5 times 4. I still have the 2. And C5, 3 is 10. That is, there are 3 ways of selecting. There are 10 ways, sorry, of selecting 3 from 5. So in the game we alluded to before, if there are 5 people in the room and 3 are selected to go out, then there are 10 ways to do that. Of course, selecting 3 to go out is the same as selecting the 2 to stay in the room. So the number of ways you can select 2 from 5 must also be 10. In fact, C5, 2 here n is 5, r is 2, so factorial is 2 factorial. And now n minus r is 3 factorial, so you get the identical thing. In fact, this proves that C nr is the same as C n minus r. For example, C7, 2 is the same as C7, 5. C11, 8 is the same as C11, 3. Let's try one more. How much is C 8, 5, say? C 8, 5. So we have n is 8, r is 5. So it's 8 factorial over 5 factorial, 3 factorial. The 8 factorial and the 5 factorial partially cancel each other out. And you're left with 8 times 7 times 6, but you still have the 3 factorial. How about C8, 8? Well, according to the formula, it's n factorial, which is 8 factorial, divided by r factorial. Now, n minus r is 0 factorial, which we said was 1. So you have 8 factorial over 8 factorial, so that's just 1. And that makes sense because it says the number of selections you can make, 8 out of 8, is 1. You just have to choose everybody. It's the only way to choose 8 out of 8. You will only have that one single choice for 8 out of 8. Now we can combine this combination formula with our counting principle, our multiplication rule. Suppose I had 5 A's and 6 B's. And again, the letters can stand for anything. It doesn't have to be letters. Number of ways to choose 3 A's and 2 B's. How many ways can I choose 3 A's and 2 B's? Well, the A's can only be selected from the A's. So the first part of the problem is how many ways can I select the A's? And that is C, 5, 3. I'm selecting 3 A's from 5 A's. Times, because even after I've made my A selection, I still have my B selection to make. 2 B's from 6 B's. So it's C53 times C62. Now you may wonder, isn't there some interaction here? How can I just multiply these independently? But in fact, they are independent. Because there's no way I could choose the A's from the B's or the B's from the A's. The rule is kind can only be selected from like kind. You can't choose a kind from a different kind. If I'm selecting A's, they can only be selected from the A's. If I were selecting letters, then I could choose from the A's and B's. But once I say 3 A's and 2 B's, the A's must be selected from the A's, B's from the B's. And I have 2 procedures to do. So the total number of ways I can do them is this procedure, number of ways in this procedure, times number of ways in this procedure. Now these numbers are 10. This comes out to be 10, we've already seen. This comes out to be 15, 150 ways. Let's just check this one. That's nr, so it's n factorial over r factorial, n minus r factorial. And you see that C62 is 15. So we have 10 times 15 equals 150. Let's take another example. How many combinations are there of 4 vowels and 1 consonant from the alphabet? And the answer is, I have in the alphabet 5 vowels and 21 consonants. So if I want to choose 4 vowels, I can only choose the vowels from the vowels, and that gives me C, 5, 4. N is 5, R is 4. And to choose 1 consonant, I can only choose that from the consonants, C21, 1. C54 is 5 factorial over 4 factorial, 1 factorial. And this is 21 factorial over 1 factorial, 20 factorial. The 1 factorial I could just ignore because multiplying or dividing by 1 doesn't change anything. The 5 factorial and the 4 factorial, the only thing surviving that will be a 5 and the 21 factorial and the 20 factorial, part of this will cancel out, and all I will have is a 21 on top. And the answer is there are 105 ways of picking 4 vowels and 1 consonant. Now, this is not with regard to order. If I were looking at order, it would be a completely different thing. This is just which letters are included, but not how they are ordered. One more example. A card deck has 52 cards, 13 spades, 13 hearts, 13 diamonds, and 13 clubs. In the game of bridge, you deal out a hand of 13 cards. Suppose 13 cards are selected. How many ways could you have a hand to have, let's say, 5 spades, 4 hearts, 3 diamonds, and 1 club? That gives me 13 cards. Now again, by the principle of kind can only be selected from like kind, I can only choose my spades from the spades, etc. So to choose the spades, it's C 13, 5. To choose the hearts, C 13, 4. And I multiply because I still use my counting principle. And the diamonds, C 13, 3. And the clubs, C 13, 1. That's the total number of ways. Okay, we won't compute that, but that certainly can be computed with our formula. Just a notation, CNR in many texts is also called CNR like that. And in more advanced mathematics, it's just written with this symbol. That is a large parentheses with N on top and R on the bottom. They all mean the same thing, namely N factorial over R factorial N minus R factorial. Now you have to ask yourself, if you see a problem, does this problem want permutations or combinations? And to answer that, you have to ask yourself, is the order important? Would it change anything if I changed the order? So for example, in the case of the 3 people going out, the order doesn't change, that's a combination. But suppose you want to arrange 3 stripes to make a flag out of 10, in that case the order is important. Or you want to make code words, in that case the ordering is important, then you would use permutations. So to decide whether to use PNR or CNR, ask yourself if the order is important or not. Now at this point, you may stop the tape if you wish. I would just like to go on and derive the 2 formulas that we spoke about. One is CNR, and the other is PN semicolon R1, R2, etc. Okay? All right. Let's see how we would derive the CNR formula. Now I know that PNR is N factorial over N minus R factorial. That one we derived already. We know that one. And what we want is CNR. Now even though we know PNR, we're going to assume for a moment that we don't know it and see how would we get at this formula? How would we get at the number of permutations without knowing this formula? I would argue like this. And let me take an example again. Suppose I wanted 2 from 4. How many ways can you permute 2 from 4? One way to do it would be the following. Let's say the 4 are A, B, C, D. One way to do it would be to list the number of combinations first, and these are A, B, A, C, A, D, B, C, B, D, C, D. So we have 6 combinations. But each one of these could be permuted in 2 factorial ways. AB, BA, AC, CA, AD, DA, BC, CB, BD, DB, CD, DC. How did I get these 12? Because I multiplied by the number of ways each of these could be permuted. In the case of 2, it's just 2 factorial. So we take my 6 combinations, multiply by 2 factorial, since each of these is 2 letters, and get 12. If I did it with 3, let's say 3 out of 5, how would I get the number of permutations? Well, let's say I had A, B, C, D, E. I would list the 10 combinations. All right. The 10 ways of listing this, just the combinations, are A, B, C, A, B, D, A, B, E, A, C, D, A, C, E, A, D, E, B, C, D, BCE, BDE, and CDE. Of course, I'm trying to develop a formula for knowing there are 10, but we're doing it indirectly. Now, how many permutations would I have? Well, these 10 combinations would be multiplied by 6, because each of these has 6 permutations. This is 3 different objects. Now, what is 6? How do I get 6? I get it because I have 3 factorial is 6. 10 combinations times 6, you get 60 permutations. And in general, it works like this. To get the number of permutations, which I'm assuming for the moment I don't have a formula for, I would start out with listing my combinations, which also I don't have a formula for right now. Multiply it by r factorial, because for each of the r elements I have this many permutations, and that would give me the number of permutations. But the truth is I do know the formula for PNR. I happen to know that this is n factorial over n minus r factorial. So to get CNR by itself, all I will do is divide by r factorial. And that's our combinations formula. So that's a derivation of that. Now let's derive the other permutation formula, Pn, R1, R2, etc. Okay, again, let's take a couple of cases with numbers, and then we'll go to the general case. Suppose I had 3 A's. This is derivation. Suppose I had 3 A's and 2 B's to permute. One way to do it would be to see where can I place the A's. Once I place the A's, then the B's follows. I don't have to choose them anymore. So one way to get this is simply to choose where the A's go, and the A's can go in 3 of these positions. If I just choose the positions where the A's go, that sets all my permutations. For example, the A's might go here and here and there. How many ways can I choose? 3 out of 5, and the B's then are forced. So this is 5 factorial over 3 factorial, 2 factorial. Suppose I had, well, let's take an example here. Now I had 4 A's, 3 B's, and 2 C's. So I have 4, 7, 9 places. And the first thing I could do is choose the 4 places for my A's. Then I must choose from the remaining 5 places the places for the B's. And I have no more choices for the C's, they're forced. So how much is this? That's 9 factorial over 4 factorial times 5 factorial. That's this one here, multiplied by 5 factorial over 3 factorial, 2 factorial. Again, let me put this here. That's C9 4, sorry, times C5 3. But you see what happens now. The 5's cancel out, and I get 9 factorial over 4 factorial, 3 factorial, 2 factorial. And if you remember the formula, that's what P9, 4, 3, 2 would be. 9 factorial, 4 factorial, 3 factorial, 2 factorial. Let's take the general case, where you have n objects, R1 of one kind, R2 of another, all the way up to R sub t, where, of course, n equals the sum of these. Just like over here, n, which is 9, equals the sum of 4 plus 3 plus 2. N is the sum of all these r's. So how do I get the number of permutations? I consider the same thing. I have n places. First, let me place all the R1 kind. So there are this many ways to place the R1s. Now there are only n minus R1 spaces left, and I have to place the R2s. Now there are only n minus R1 minus R2 places left, and I have to place the R3s. And I do this all the way down to all the way to here, and RT minus 1. I don't have to worry about the teeth kind. That's going to be forced. That's how far I have to go. So let's see what that's equal to. This is n factorial over R1 factorial, n minus R1 factorial. That's this one. and this is n minus r1 factorial over r2 factorial. Now it's the difference of these two, so it's n minus r1 minus r2 factorial, which is what the next one starts off with, n minus r1 minus r2 factorial, r3 factorial, and the difference all the way down to over rt minus 1 factorial and n minus r1 minus r2 minus r all the way to rt minus 2 minus rt minus 1. I still have to subtract that one factorial. So you see that many things will cancel here. This is going to cancel this. This will cancel this. This will cancel whatever the next one is. And this here will cancel this one. And what am I left with? Well, what is this? If you take n, subtract everything but the last one, you're just left with r sub t. So this is r sub t factorial. And I have n factorial on top, r1 factorial, r2 factorial, all the way to rt factorial. And that's my formula for p n semicolon r1, r2 up to rt. That's my permutation formula. This is often called a multinomial coefficient. Okay, that ends this lecture.